Topological sorting, often referred to as topological order, is a fundamental concept in graph theory, primarily applied to directed acyclic graphs, DAGs. The primary purpose of topological sorting is to arrange the vertices of a graph in a linear order, such that for every directed edge, u, v, vertex u comes before vertex v in the ordering. In other words, topological sorting provides a way of ordering the vertices such that the constraints represented by the directed edges are respected. This concept plays a pivotal role in a variety of fields, such as task scheduling, dependency resolution, and compiler optimizations, making it a crucial tool in both theoretical and practical applications. However, it's important to note that topological sorting is only applicable to directed acyclic graphs. If a graph contains cycles, a topological ordering is not possible, as there would be no way to order the vertices to satisfy the constraints. The key properties of topological sorting stem from the structure of directed acyclic graphs. In a DAG, there are no cycles, meaning that there are no circular dependencies among the vertices. This feature is essential because, without acyclic constraints, the problem of ordering vertices would be unsolvable. A DAG can represent many real-world situations where certain tasks must be completed before others, such as in scheduling, project management, or resolving dependencies between software packages. In these scenarios, topological sorting provides a clear, linear order that ensures that each task is completed in the correct sequence, respecting all the precedence constraints. A topological sort is not unique. A graph can have multiple valid topological orderings. For example, in a situation where there are multiple vertices that do not depend on each other, they could be ordered in any order while still maintaining the correctness of the sort. Despite the possible variations, each valid topological sort respects the condition that for every directed edge, u, v, u must precede v in the order. This flexibility is particularly useful when there is more than one valid way to schedule or order tasks. The algorithm for topological sorting depends on the specific structure of the graph and can be implemented in different ways. The most common methods to perform topological sorting are Kahn's algorithm, which uses in degree of vertices, and a depth-first search, DFS, based approach. Kahn's algorithm. Kahn's algorithm is an efficient approach to topological sorting that leverages the concept of in degrees. The in degree of a vertex is the number of edges directed into it. In Kahn's algorithm, the process begins by identifying all vertices with 0 in degrees, meaning that they have no incoming edges and can therefore be placed at the beginning of the topological order. These vertices are added to a queue or list, and as each vertex is removed from the queue and added to the topological order, its outgoing edges are examined. For each outgoing edge, u, v, the in degree of vertex v is decremented by 1. If any vertex's in degree reaches 0 as a result, it is added to the queue. This process continues until all vertices have been processed, and the topological sort is complete. One important feature of Kahn's algorithm is that if, at any point, there are still vertices with non-zero in degrees and the queue becomes empty, it indicates that the graph contains a cycle. In such a case, topological sorting is not possible. This detection of cycles is a built-in advantage of Kahn's algorithm, making it an efficient way to both sort the graph and check for cycles simultaneously. The time complexity of Kahn's algorithm is O, v plus e, where v is the number of vertices and e is the number of edges, which makes it optimal for sparse and dense graphs alike. DFS-based topological sorting. Another common approach for topological sorting is based on depth-first search, DFS. In this method, A DFS traversal is used to explore the graph, and vertices are placed into a stack in the reverse order of their finishing times. The idea is to explore the graph deeply, visiting each vertex and recursively visiting its neighbors. As the DFS reaches a vertex with no unvisited neighbors, a leaf node, it finishes and is pushed onto the stack. This ensures that when the DFS finishes exploring a vertex and all its descendants, the vertex is placed into the stack only after all of its dependencies have been fully processed. Once the DFS traversal is complete, the stack will contain the vertices in topologically sorted order. The stack is then popped to retrieve the final order. As with Kahn's algorithm, if the graph contains a cycle, the DFS will encounter back edges, indicating the presence of a cycle, and a topological sort will not be possible. The DFS-based approach is also efficient, with a time complexity of O(V+E), as each vertex and edge is processed once. It's particularly useful in scenarios where a full-depth first traversal is required or when dealing with recursive problems. Applications of topological sorting. Topological sorting has a wide range of practical applications in fields like computer science, project management, and operations research. One of the most well-known applications is in task scheduling, where certain tasks depend on the completion of others. For example, in software development, compiling code often requires that certain modules or libraries be compiled before others, making it a typical use case for topological sorting. By representing tasks as vertices and dependencies as directed edges, topological sorting provides a clear, linear order in which tasks should be executed to ensure that all dependencies are respected. In project management, particularly in the context of dependency resolution, topological sorting is used to schedule tasks based on their precedence relationships. This is often done using tools like Gantt charts, which visually represent task dependencies, or through the use of algorithms that compute the optimal order in which tasks should be completed. Similarly, in build systems, topological sorting helps manage the sequence of operations required to build a project from source code, where certain files must be compiled before others. Topological sorting is also used in compiler optimizations for processing source code. Many compilers use topological sorting to resolve dependencies between different parts of a program, such as during register allocation, instruction scheduling, or dependency analysis. Additionally, topological sorting is helpful in data flow analysis, where variables in a program are analyzed based on their dependencies to optimize performance. Another interesting application of topological sorting is in version control systems, such as Git. When merging different branches of a project, Git uses a form of topological sorting to reconcile the changes and determine the correct order in which they should be applied. This ensures that no changes are lost, and dependencies between different versions of files are respected. Topological sorting is a critical algorithmic technique for dealing with directed acyclic graphs, DAGs, enabling the linear ordering of vertices that respects dependency constraints. It finds wide applications in areas such as task scheduling, project management, compiler optimization, and dependency resolution. Both Kahn's algorithm and the DFS-based approach offer efficient methods for performing topological sorting, with a time complexity of O(V+E). The flexibility of topological sorting, in that it can handle multiple valid orderings and detect cycles, makes it an invaluable tool in both theoretical and real-world scenarios. Whether used in the context of software development, project management, or network analysis, topological sorting remains a vital algorithm for organizing tasks, resolving dependencies, and ensuring the correct order of operations in complex systems.